Hello everyone, today I'm going to talk about methods of reconstruction of non-Cartesian data. There are many ways to reconstruct data from the spatial frequency domain. Instead of reconstruction, resampling data first, which is in the non-Cartesian domain, and then reconstructing it on the Cartesian domain is a more efficient way. There are three categories of resampling. These are grid-driven, data-driven, and optimum interpolations. Grid-driven interpolation is easy to implement and does not require a density estimate because it does not use all the data from all the grid points. However, it's comparatively more SNR inefficient. Projection reconstruction is an example of grid-driven interpolation. However, it's not widely used in practice. Here you can see some of the grid-driven interpolation methods. Bilinear and bicubic are popular examples of this. Bilinear is simpler to implement, however, it does not create higher fidelity images compared to bicubic. Yet, bicubic imaging creates a less detailed version of the original image. And here you can see how grid-driven interpolation works, where data is retrieved from its neighbors. Data-driven interpolation uses a convolution kernel. This kernel is uniform for all grid points. Compared to grid-driven, this method is more SNR efficient. Gridding is an example of data-driven interpolation. Here you can see the basic principle of gridding. Now I'm going to show the formulation of the gridding method. Here you can see all the steps in use. This is the sampler in non-Cartesian domain. The acquired data is after being sampled is convolved with the gridding kernel function. Then this expression is resampled on the Cartesian grid. After taking the inverse Fourier transform of this expression, the result is obtained. Here, the convolution kernel function would be equal to sinc function, thus making its inverse Fourier transform a rectangular function. However, since the sinc function is extended to infinity, this cannot be applied in real life. Therefore, a windowed sinc function is used instead. Now, continuing on the presentation, you can see the basic principle of data-driven interpolation on a spatial frequency domain. This is the convolution kernel that we are using. Now, we're going to have a demonstration of this. Here, basically, the blue squares represent the Cartesian grid, whereas the white squares represent the non-Cartesian grid. You basically look at each point in a uniform way. This is the same example from another point of view. The fact that they are heightened is only an indicator to show that they're the ones being neighbored by the grid point. Continuing on with the presentation. Now, let's talk about optimum interpolation. In optimum interpolation, unlike the data-driven interpolation method, the kernel size and the kernel interpolation function are determined uniquely for each grid point. Bursts, regularization bursts, and NUFFT are some of the algorithms that's being in use. Here, the red area represents the neighboring points in the Cartesian domain, whereas the white squares, which are highlighted, represent the neighboring points in the non-Cartesian domain. As you can see, their sizes are different. Now, we're going to talk about the formulation of this method. Formulation of this method is rather more complex than the data-driven. Here, for any point in the Cartesian domain Ki, we define Mi is the area with the white squares, which is the sampled neighboring points of Ki in non-Cartesian domain, whereas Ni is the area with the blue squares where it's the Cartesian neighboring points of Ki. And these two expressions are the radii of the previous neighboring points mentioned. We first define an m by n interpolation coefficient matrix A using sinc interpolation. Then we compute the pseudo-inverse of this matrix and transfer its ki row to the ith row of AP. And then we take the inverse Fourier transform of this linear equation. In order to use arbors, which helps us get rid of small perturbations since it's less sensitive to them, we, instead of taking this linear equation, we take this. This is its approximate solution, where this expression is the positive soothing parameter. When it goes to 0, it equals to the Bur's equation. Continuing on with the presentation, now we have a demo for this method. Here you can see the convolution kernel moving in the Cartesian domain. The change in size is not accurate, and it's only to show that it's not the size but the convolution kernel function is the one that's in change. The size obviously is fixed. We can look at this from a different angle. Here you can see how the convolution kernels respond to each point in a different way. Again, the change in size is only a representative and is not what it actually is. Continuing on with the presentation, you can see some of the results obtained. All of these pictures were retrieved using the Bur's algorithm. Here you can see that each pair has different values. This is to show the difference between using different kernel sizes. The first, the third, the fifth, and the seventh pictures use a different kernel shape than the rest. They are made using circular kernel shapes. You can see that compared to square, they have more detail within. Using a circular neighborhood results in more true-to-life images. Here, you can see that all of these pictures were obtained using Bur's algorithm. It's already apparent that this algorithm creates much clearer and less distorted images compared to Bur's algorithm, which was shown in the previous slide. This is an extreme example where values are way higher than they should be. In the first picture, you see the actual original picture, and the second and the third are rendered using Bur's algorithm. The one in the middle is square, and the one on the right is circular neighborhoods. You can see that the circular neighborhood creates slightly more natural ones compared to square neighborhood shapes. Here you can see the general difference between the Bur's and the Bur's algorithm. The pictures that's created using Bur's are subpar compared to Bur's. For example, for these two same values, the Bur's algorithm picture is not definable at all, whereas you can clearly see a lot of detail in Bur's algorithm. This is the end of my presentation. Thank you for listening.